Welcome everyone. We're going to pick up where the last video ended with a new equation. So as we're working through these kinematic equations, it's important for us to not only understand how to use them, but to understand when to use them. That's one of the big challenges in the kinematics unit. There are a lot of formulas, and picking the right one is often challenging. We'll practice that in a little bit, but let's start by looking at the next kinematic equation. And that kinematic equation will allow you to calculate the final velocity of an object given its acceleration and the time over which it is accelerating. So that is going to look like Vf for V final equals Vi, V initial, plus A acceleration times delta t time. And this comes from the definition of acceleration. So I'll show you the derivation really quickly. If we start with A equals delta V over delta t, that can also be written as Vf minus Vi over delta t. So if we have A equals Vf minus Vi over delta t, if we want to rearrange this so that we get Vf on its own, we're going to multiply by delta t on both sides. We get A delta t equals Vf minus Vi. If we add Vi on both sides, we get Vf, these cancel, Vf equals Vi plus A delta t. So that's where it comes from. Let's go ahead and use this. So we're going to use the velocity calculation formula to solve a problem. A car with an initial speed of 7 meters per second accelerates at a uniform rate of 2 meters per second squared for 4 seconds. What is the final speed of the car? So let's do that. We're going to start, as always, by listing the information that we are provided. So the initial speed, we're going to call, that's our Vi, and that's our 7 meters per second. Oops. Come on. And it accelerates at a uniform rate, so acceleration of 2 meters per second squared for a time of 4 seconds. And what we're asked to find is what is the final speed, Vf, of the car. That's our unknown. So if we're going to move forward with this problem, we need to list some formulas, right? We just listed all of our stuff. Now we need formulas. So what do we know? Well, we know that V equals delta x over delta t. We know that A equals delta V over delta t. We know that delta x equals 1/2 Vi plus Vf delta t. And we just learned that Vf equals Vi plus A delta t. So we are told that we are going to use the velocity calculation formula, but let's just make sure that we have everything we need in order to do that. So, first of all, does it solve for Vf? Yes, it does. Does it have Vi? Yes, we do. Do we have A? Yes, we do. Do we have delta t? Yes, we do. So we are ready to move forward. So we'll start with the formula itself. Vf equals Vi plus A delta t. And now we can fill in the information we know. Vf equals Vi 7 plus A 2 times delta t 4. So if we have Vf equals 7 plus 2 times 4 is 8. So our Vf equals 15 meters per second. All right. So did we answer the question that we were told to solve for? Yes, we did. We found Vf. So we are all set. Okay. Now, the next thing we're going to talk about is falling objects. So falling objects are not particularly too difficult to understand conceptually. I mean, I'm sure you've all dropped something, and we have looked at falling objects a little bit in the forces unit, but here we're going to talk about them in terms of kinematics. So objects fall on Earth with a constant acceleration that we call lowercase g, where g is a negative 9.8 meters per second squared. That's its acceleration. So what that means is that every falling object, for every second that it falls, it will increase by 9.8 meters per second worth of velocity. So if it falls for 1 second, it's going to obtain 9.8 meters per second of velocity. If it falls for 2 seconds, it's going to obtain twice that. 3 seconds, 3 times that, and so on. And it also works for fractions, right? You can multiply 9.8 by 1.5 or 2 3/4, whatever it might be. 2.7, 3.8. But what we can do is we can use this constant acceleration to determine the properties of an object in motion. So we're going to do falling object problems, and whenever we see an object that is either let go and dropped down or thrown up, we're going to have to make the assumption that as long as we're on Earth, it's accelerating at g equals negative 9.8 meters per second squared. So as you may remember from our actual kinematics unit in class, there were some assumptions that we needed to make for certain problems, and the acceleration of negative 9.8 meters per second squared was one of those assumptions. So if we say a ball is dropped and falls for 2 seconds, what is its velocity right before it hits the ground? All right, so let's gather some information. So we're dropping an object. So when we see an object being dropped, our first thought should be that its acceleration is going to be negative 9.8 meters per second squared. And that negative is important because it indicates that the object is falling down, right? Typically, if we're talking up versus down, the up is positive and the down is negative, so that negative sign is important. And it's going to fall for 2 seconds, all right? That's a delta t of 2 seconds. And we want to know what is its velocity right before it hits the ground. That's going to be our VF, is our unknown. Actually, let me put that down there. Now, the last thing that we need to do is we need to start listing some formulas. So let's see, we got V equals delta X over delta T, A equals delta V over delta T. We've got delta X equals 1/2 VI plus VF delta T. And then we have VF equals VI plus A delta T. So we want the velocity right before it hits the ground. So what we're going to do is we're going to look at our formulas and decide which of them is the most useful. So first of all, we know that V equals delta X over delta T, this guy, only works for a constant velocity. This is not a constant velocity. It is accelerating under gravity, so that's out. A equals delta V over delta T might be useful. So we're going to leave that alone for now. Delta X equals 1/2 VI plus VF delta T. We have VF, or we want VF. We have delta T, but we don't have delta X, so we don't have enough information to use this. If we look up here again at that A equals delta V over delta T, it's actually very similar. We derived this second equation from the first one. So really they're identical. I'm just going to go ahead and cross that out because it doesn't directly solve for what we want. We can see over here that this equation directly solves for VF, so it's going to be the easiest for us to use. Let's check that we have everything we want. I'm going to go right to left. Do we have delta T? Yes, we do. Do we have A? Yes, we do. Now, we run into this here, VI. So in this case, we need to make a second assumption about a falling object. So what do we know about what this object is doing? So it says an object is dropped. So if I drop an object, yes, I know that it's going to accelerate under gravity. But the other thing I can assume about a dropped object is its v initial is going to be 0. If I drop something, I'm not giving it any initial velocity. All I'm doing is allowing it to accelerate under the influence of gravity. So now that we've made that assumption, do we have VI? Yes, we do. Does it solve for VF? Yes, so we're good to go. So let's do that. So we have VF equals VI plus A delta T. So VF equals VI of 0 plus A of negative 9.8 delta T of 2 seconds. So we end up with the 0 drops out. So we get a VF equals negative 9.8 times 2. And that works out to be a final velocity of negative 19.6 meters per second. That negative sign indicates that it is moving downward, which we know is true. For a dropped object, have we answered the question? Yes, we have. Cool. Let's do another one. We're going to kind of work in the opposite direction. So a ball is dropped from rest. Its final velocity right before it hits the ground is measured at negative 10 meters per second. How long did the ball fall? So I will tell you ahead of time, and while I do this problem, you will see that we are going to work backwards in order to solve this problem. We're going to have to use our physicsy brains to rearrange a formula, or at least be able to understand how to work a formula backwards. This is an algebra skill as much as it is a physics skill. So let's go ahead and assume the two things that we need to assume about dropped objects. The ball is dropped from rest. If it's dropped, that means its acceleration is going to be negative 9.8 meters per second squared. If we're dropping from rest, that means our VI is 0. And its final velocity right before it hits the ground is measured at negative 10. So that means its VF is negative 10 meters per second. What we are asked is how long does the ball fall, meaning delta T is our unknown. So now we're going to list our formulas as we do. I'm just going to jump right ahead and use our slightly more specific ones. I'm going to skip the the V and the A definitions. So delta x equals 1/2 VI plus VF delta T, and VF equals VI plus A delta T. So which of these is usable? We know A, so is A anywhere in this equation? No, it is not. We are also not told what the displacement of the object is, the delta x. So this one is going to be out, which means this is our winner. All right, so let's go ahead and use it. We have VF equals VI plus A delta T. Let's fill in what we know. The VF is a negative 10, and that equals a VI of 0 plus an A of negative 9.8 times delta T. So that 0 drops out. We are left with negative 10 equals negative 9.8 delta T. So if we divide by negative 9.8, we get a delta T of, bear with me, 1.02 seconds. Have we answered the question? Yes, we have, and we are good to go. All right, let's move on. We're going to put a pause right here, and we're going to resume in the next video where I solve this problem. Car accelerating at a constant rate. traveling a certain distance, and we're looking for the time. So I'll pick that up in the next video. See you then.